will be organizing it with hopefully a number of people here who will help. So yeah, with February 2024, that's the plan for now. Of course, the plan is to have it in person this time. We may or may not have an online component, but we definitely are planning for in person. So please prepare to come to Dunedin in February 2024. So we'll also have that same year. It looks like we're also going to organize the New Zealand Fluid Mechanics Conference, probably around the same time. So for the people who want to come to both, we'll probably coordinate that as well to make sure they are one after the other. All right, so yeah, that's pretty much all I have to say. Of course, I don't have any details yet on the dates or anything like that, but you'll hear from me in the near future. All right, so let me introduce now our first speaker. We have Professor Karin Bryan from the University of Waikato in Hamilton, New Zealand. And so Professor Bryan is an expert on coastal processes. And today she's going to talk to us about wave theory and planning for coastal adaptation.
Let's go. Okay, just a sec. Okay, hopefully everyone sees the presentation. Oh, good. Okay, hi everyone. Thank you to the organizers for inviting me to give the presentation. I've been looking through the talks with interest, and I see a few familiar faces and quite a broad range of talks on waves. The talk I've prepared is probably going to be a bit different because I haven't done a lot of detail into the different aspects of things we're working, but hopefully it will be interesting and set some scenes and ideas for people. Okay, I think one of the main things about being a coastal scientist and engineer at the moment is that we're being tasked with helping to prepare for sea level rise and to a lesser extent climate change. And that means either addressing flooding or erosion, the two big topics that are involved in adaptation. Now, being a waves person, I'm immediately attracted to the open coast erosion questions. And I guess that's because the physics is more interesting. There are very high levels of energy in the open coast, which means there are a lot more things like nonlinear transfers and that kind of thing. So we're looking at those timescales, and swell and storm waves, and those create surf zone processes, and extreme tides and storm surges become important. Flooding, on the other hand, generally affects low-lying land and often in estuaries and inlets, and needs to look at different timescales and different types. In this talk, I'm going to talk about flooding and focus on flooding. Now, the reason for that is, why do we focus on flooding? Why do I think it's important to focus on flooding? Well, to me, the solution for open coast erosion is quite simple. Don't live in a section that is too close to the front of the beach. Otherwise, you're going to have to move. Of course, that's my personal opinion. On the other hand, the environmental effects of low-lying coastal flooding are really quite broad-reaching, and how the flooding and the tide interact with low-lying land. How do we protect this valuable land? These are really interesting questions, societal questions. Things that are important about them is that a large amount of carbon is stored in mangroves and salt marshes and even in the low-lying land. Intertidal regions actually support a whole wide range of ecosystem services that sit at the base of the food chain that we rely on estuaries as our food baskets. Low-lying land in New Zealand is excellent for farming, being the recipient of floodwaters for many, many years. It's built up stores of nutrients, and the soil is usually very rich there. And it's very susceptible to flooding, and there's lots of studies on the coastal squeeze and whether or not the coastal area will be able to migrate freely shorewards as sea level rises. Okay. So basically, we have two approaches to modeling the fate of this land. One is to do dynamically accurate models, and there are a number of options available like Delft 3D and Mike. unfortunately, these models really simplify the sediment and ecological processes and generally can't be run on very large spatial and temporal scales needed to create adaptation plans. The other option is to do very simplistic hydrodynamic model, a very simplified version of the hydrodynamics and a much more complex approach for the other processes, the ecology, the sediment characteristics, the compaction and the tree growth, all that stuff. And in these kinds of models, the hydrodynamics is most often represented by the bathtub approach, where the tide just fills the contours up to the high tide line. Now that approach works really well for mean sea level changes, but anything like surge or tide, anything that's a wave, you need not only to be able to conserve mass, you also need to consider momentum. And so I'll show you an example. This is from Breda, who's a PhD student at University of Newcastle with Jose Rodriguez and his group there working there. And this is the first paper from his PhD. And he takes a very simplistic model grid to represent an intertidal area. And he looks at evolution using that simple model grid and compares it to the bathtub approach. And he does different simplifications of the model grid, but this is the main result. And so you can see this is the accumulated accretion of sediment on the intertidal area in the model. And you can see that the bathtub approach actually provides completely different results. Okay, so using this as an approach to actually specifically plan adaptation in a very particular region, it really becomes quite questionable. The aim of this presentation, we obviously need to balance our level of simplicity with the hydrodynamics and the level of simplicity with all the other things that need to be modeled. And I argue that there are some aspects of wave behavior that you simply can't ignore. So the aim is to use examples of field and numerical modeling studies from around New Zealand and overseas. I've done a little bit of work overseas to show how the momentum balance in waves actually determines how low-lying coastal land might adapt to climate change. So it's not just bathtub approach. And the key things that I'm going to highlight are attenuation, asymmetry, which is essentially nonlinear transfers of energy, storage or accommodation space, and finally talk a little bit about channelization in these regions and what that does. The study sites, this is my couple of fun slides. We've been working on a number of sites in the North Island of New Zealand, and they are in the areas that are dominated by mangroves. So one of them's in the Hauraki Gulf here and in this big mangrove area, which has got quite a simple geometry, and the mangroves are about 1 kilometer wide. And other than that, it's basically a big mud flat. You can see a picture of it here. Here's a profile through that site. So you can see this is seaward, and then it ramps up into the treed region, and then it's basically flat topped. So there's a sharp increase in the gradient across the fringe. And that, of course, with the mangroves means that there's an increase in friction that's very common in these environments. The other site that I'll mention a little bit is from work that we did in the Mekong Delta in Vietnam. And I'm talking about the royal we here because I didn't actually do the field work, but my colleagues did. And you can see that some of our experimental setup, and we set up experiments on these transects on both sides of this, I guess it's a river bank. Big scale riverbank. That's the scale there. Okay, so those kinds of sites are very similar, and I'd argue that they're very representative of these kinds of systems globally. And in fact, I've gone through a lot of different publications to look at how profiles look in different areas around the world. And where's our site up there? Actually, I can't remember which one's ours. I think. Oh, it's not pictured here, but it's very similar. They tend to be quite flat topped in the treed or vegetated region and then drop off steeply on the seaward region. Unless the vegetation, like over here, oh, this is one of our sites, is very sparse, and then it tends to be more gradual. Okay, so starting out with attenuation, I just love this video and I show it all the time. So I'm going to play it. It's from Deltares and it's available on YouTube. And it shows a simple wave flume with trees in it. And if you run it, it's a bit noisy, sorry. You can very clearly see by the time you get to the other side of the tank, there's almost no wave energy left at all. Okay, so definitely the vegetation has a strong role in attenuating the wave energy. So this is the first example of data collection I want to show you. And in this case, we instrumented across this vegetated flat in the Firth of Thames, and each one of these represents a water level recorder. And we did this during one of the storm surge events, which was a 1 in 50-year tidal event compounded by a storm. And that gave a fairly high water level. So these here are the location of the recordings. And you can see here they're plotted on top of each other and kind of zoomed in. And you can see the turquoise one here is the outer station. And as you moved in towards the inner station, that storm surge peak was attenuated by about 25 to 30%. And so here is plotting out the amplitude of the peak for all of these events, and from the seaward side to the landward side, and plotting some simple attenuation models on there, and you can see that quite well predicted by those. The attenuation is very frequency dependent, and that example from the Deltares wave flume works particularly well because the waves are such high frequency and are attenuated the most. Here are measurements from the Vietnam experiments where we measured wave conditions outside, at the fringe, and inside the forest. And here they are plotted. So you can see outside the lower frequencies. So this brown line is from the mudflat, the lighter green line is from the fringe, and the forest one is the higher line. So you can see that the higher frequencies are very much more attenuated by the vegetation than the lower frequencies. You can also see this vertically, and here we do some high resolution measurements here with using Vectorino current meters, and that's the lower one and that's the upper one there, and we're looking at, these are pneumatophores of Sonataria, which is the mangroves that grow in that region on the seaward fringe. So if you look at the spectra from the higher observation point and the lower observation point, you can see that the higher frequencies are very much more attenuated in the vertical as well. So the one that's close to the boundary layer has much lower high frequency measurements than the upper one. And you can see there's the gain, and there are also some phase shifts. So that attenuation is very, very sensitive to the frequency of the waves that you're measuring. And you see a lot of studies on eco-defense and eco-defense solutions, and they very roughly say, oh, well, vegetation just attenuates storm waves by how much, but it really, really depends on the frequency of those waves. And the things you look at, the conclusions you come to for wind waves are very much different for surge. And so we can confirm that with numerical modeling, and this is with the Delft model set up across the same mangrove fringe, the same site. And here you can see this is seaward up here, and this is landward up here. And here's the water level, high tide, and then it drains out, high tide, and then it drains out. And see, as you can move across the fringe of the mangroves, you can see that there's strong attenuation, which is matched by the observations. So the interesting thing about the model and doing things with the model is you can remove the vegetation in a way that you can't do in a real setting. Well, not without a lot of consents. Well, I don't know, mangroves you're allowed to move in some cases in New Zealand. But in general, it's very difficult to take out the vegetation because the immediate assumption is that the reduction in water level and the attenuation shoreward is because of the role of the vegetation. But in fact, if you take the vegetation out, the green line here compared to the blue line, it's still attenuated. So it's simply yes, there's an added attenuation due to the vegetation, but it's also simply that it's getting shallower and friction depends on the depth of the water. And there's the currents on this side. So how do you measure, as a matter of interest, people always ask, how is Delft 3D, how does it model vegetation? Because generally these are 2D models. And so how does it incorporate a vertically varying vegetation in a 2D model? And the way we mostly use is what we call the Baptiste formulation, which is basically it has two different adjustment factors. One, when the water is pushed through the vegetation and the vegetation exceeds the water level, and then another when the water level is greater than the vegetation, in which case it partitions the water level into the upper and lower region. And it allows for some, depending on the density of vegetation, it allows for some skimming flow. This, of course, becomes really important when you're trying to move sediment around, because sediment initiation is done by the bed shear stresses. And so if you have vegetation covering the bed shear stress, you can have quite a strong free stream flow, but it might have no effect on the bed at all. So going back to these modeling results, you can represent the water level and the currents as a stage plot, in which case the water level here is on the vertical and the currents is on the horizontal. And you can see that plotting it as a stage plot makes it very easy to see whether the ebbing currents are greater or less than the flooding currents. So here are the flooding currents on this side, and here on the ebbing currents on that side. And again, that seaward and landward, same characteristics. So you can clearly see that attenuation there, but you can also see that the asymmetry, the balance between the ebb and flooding currents changes really quite dramatically as you move up over the fringe, right? And that's associated with the shape of the tidal curve going from being like an ocean tide to being almost like a river discharge. This draining arm of the tide gets really strongly affected by friction and gets really extended out like that, which of course changes the ebb and flood current balance. So there's a complete change of shape of the tidal signature as it moves across the vegetated region. Okay, and you can see that if we plot that modeling as a stage plot in much more detail. Here we are on the seaward side, moving up over the fringe into the vegetated region, across the top of the tidal flat. You can see the attenuation there as you go in, the amplitude reduces inward, and you can see these stage plots gradually change. We've got the ebb on this side and the flood on the inner side. So out here, in the seaward end, it's very strongly ebb dominant. And as soon as you go past this point represented by the blue line, it goes flood dominant. Now I've plotted out a typical curve here so you can see what I mean, because sometimes they're hard to visualize. So moving around there. So there's kind of a split point here, and with flood dominance on the inside and ebb dominance on the outside. And that point is really, really sensitive to where the vegetation starts and where the morphology changes. Okay, so the reason for that has to do with the way the tidal wave moves into that. As the incoming tide comes, it shoals up, creating a gradient here, which pushes a flooding current into the tidal flat. And then as it drains out, if there's no vegetation, the drainage is quite easily is not impeded very much. And so you get a mild slope in the water level on the draining tide, which allows for ebb dominance. If you add trees, like in panel B here, that really slows that drainage down and makes a really strongly sloping ebbing tide, which then drives an ebb dominant flow just seaward of the fringe. And of course, panel C is meant to emphasize that really, really depends on the density of the trees and the frictional effect of the trees. Okay, for those of you who like nonlinear transfers, where does that asymmetry come from? And this is, I find quite interesting, because here I did the harmonic analysis, and you can track the amplitude of the M2, the M4, so the first harmonic, the M6, the first harmonic, second harmonic, and then the M8, the third harmonic. And so you can see that they gradually change in balance as you move up over the fringe, and the phase between them changes, and that accounts for that change in shape of the tidal wave. So what do we care about asymmetry? Why is it important? Well, that's because it has really, really strong implications to how sediment is transported into that fringing region. And of course, how that land is built, which is basically our ability to maintain the elevation of the wetland areas, the forested areas, is what's going to protect the coast from flooding. So that's absolutely critical to trying to understand how this land will adapt to how we can adapt to sea level rise. So of course the spatial gradients in currents, as the current drops off, the sediment falls out as suspension, and just the very existence of attenuation will cause an accumulation of sediment shorewards, because these are very fine sediments. It takes quite a long time for them to settle out of the water column. And so that spatial gradient can be caused by attenuation, but we also have to remember that the tide can shoal a little bit as it goes across the edge of the fringe. Oops, other way. Oop, wrong way, sorry. The next one is tidal asymmetry. And basically if the ebbing currents are stronger, which is what's happened at the fringe, that'll carry sediment seaward. And then where the flooding currents are stronger, it'll carry sediment forward. So that division between where it's flood dominant and ebb dominant is often around the slope break at the edge of the fringe. Okay, so that's individually in one transects what's happened. And you can build that into a very simplistic schematic model. And this is Baron van Manen's PhD project. And he created a big synthetic basin that's supposed to look like one of our barrier enclosed estuaries in New Zealand. These gray areas are the land, and that's the spit with a narrow entrance. And this red area is the back barrier basin where the mangroves grow. And so there are mangroves in his model. And he ran it over many, many, many decades, and the sediment responded through time. And you can see A, B, C, D is how the intertidal areas begin to infill and gradually develop channels as the ebbing and flooding currents scour out these sediments. And you can look here down at the bottom, and I think I've zoomed in on that. At the beginning, when the model starts to run, the black line here is the tidal elevation and the red is the currents. You can see it's strongly flood dominant, and that brings new sediment into the system. And then gradually through time, it evolves to the bottom panel, panel B, where the ebb and flood currents become quite similar. And that's how it adjusts to equilibrium. It does that by trying to remove the try to balance the ebb flood dominance. And so if you look at those through time as a stage plot, you can see that first of all, that the top area is flood dominant. So this is at high tide, the whole region's flood dominant. These are flood over here. And at low tide, the whole region's ebb dominant. So that's similar to what we showed in those transect models. But you can also see that with and without mangroves, the ones with mangroves are in green, and the ones without mangroves are not in green. You can see that mangroves make a really, really big difference to that flood ebb dominance. In fact, if we add in a sea level rise, and this shows my integrated elevation across the whole basin, all integrated together. And this is the aerial extent of that elevation. So we have lots of elevation that's in the shallow regions, the intertidal regions. And normally in any evolved estuary, you get deeper channel networks that are down here. And so this is the one with sea level rise. These darker ones and the lighter ones are the model runs without sea level rise. So interestingly, you can see again how important the friction and vegetation is in terms of that fringing region, which is just around here. And you can see that the mangroves actually cause that fringing region to to get shallower. So it actually allows the land to catch up with sea level rise. And there's been quite a few people that have shown that in marshlands and all sorts of different using all sorts of different modeling types. Of course, this all depends on the sediment supply that's delivered to the model. So one of the big questions that we're addressing in our next phase of work is to try and get a better handle on what a realistic sediment supply is. Okay. So let's go back to this diagram of storage space. Just going to check the time. Yep, doing well. So remember, this was the one where we measured that 1 in 50-year event across the Firth of Thames fringe at all those array of water level sensors. And one thing that you can look at, and we fitted a simple model for the attenuation, and that simple model basically balanced the friction and the storage space. So we could, which is basically the volume of space left to have to keep the water at high tide. And so because we had this very simple model, we could play around with that and see whether it was actually the friction that was causing this attenuation or the storage space. And here, basically, we try all sorts of different sizes of forest. One in which the size of the forest is only half the length of the tidal wave, one where it was about the same length as the tidal wave, one where it was twice the size, and that one in which it was 4 times. So this one where it's 4 times has a really big back barrier storage space or back mangrove storage space with plenty of space for high tide floodwaters to go. And you can see in all these examples have the same vegetation, the same amount of friction in them. But you can see it's a huge difference. Basically, this one with almost no storage space has almost no attenuation whatsoever in the first distance. That's probably around 500 meters. And so storage space is actually much more important than the frictional characteristics when you're talking about tidal waves. And that's because the tide isn't like a normal wind wave like we think of it, like in that Deltaris flume experiment. It is always a slightly reflected wave, even when there's a lot of dissipation. It always is slightly reflected. So the conditions shoreward, the boundary shoreward, makes a really big difference. So the overall size of the forest is bigger, attenuation is greater. So it's not like a wind wave. Storage capacity is more important than the dissipation in determining how much attenuation occurs. And we can middle round, and we've done further experiments. And this is this is John Montgomery's PhD. So this was his last paper, which he's still under review at the moment. And in this paper, he manipulated not the size of the storage space, but the slope of that region. And we also found that the slope was extremely important. Here's the, unfortunately, my landward, seaward's the other way around. But this is basically the reduction in peak water level as you move from the fringe over here to in the forest. And you can see it's very, very sensitive to slope. The no slope version was a little weird, so that's why they're not in a progression. But of course, because the no slope version has to have a back wall in the model, right, for it to be modeled. And I think that's the effect of the water reaching that back wall. Okay, so that's storage space. What's next? So the shape of the profile and how it might evolve is critically important to that attenuation and also the balance of ebb and flood currents that we talked about earlier. So the last thing I want to talk about is, almost last thing I want to talk about is the channels. Now, the channels end up really being very, very important as well. And it's often in those, again, I'm going back to the simplistic views of eco-defense that just say, oh, if we have 500 meters of mangroves, we're safe from storms. If we have a kilometer of mangroves, we're really safe from storms. Well, that would, of course, be true in the Firth of Thames, where our mangroves are very, very consistent and we don't have a lot of channels, and the forest is quite similar density everywhere. So that's that site. And here's our array across our transect. But we went to another site, which was further south in Tauranga Harbor, which actually has really, really quite dense shrubby mangroves, right? And these ones, when the tide comes through the Firth of Thames ones, it actually really ends up going through the stems of the forest because the trees are quite high. But in Tauranga Harbour, the mangroves are much shorter and they're really convoluted and they lie across the sediment. So we assume that they would be extremely frictionally important. So we went out and put our water level sensors out there thinking, this is going to be a great example of a frictional attenuation. Very exciting. Unfortunately, that didn't happen at all. So the top two panels, panel A and B, they show the Firth site that you've seen before. And the bottom two panels show a tide in this new site. And you can see there was almost no attenuation at all, almost tiny, tiny amounts of attenuation, even though the size of the forest is actually quite similar. And of course, it doesn't take a rocket scientist to see that this place is really heavily channelized, that there are channels coming up both sides. And so we set up numerical models for these regions, this region, and so that we could take out the channels and put in the channels, and found, of course, that if we take out of the channels, the model, we actually get the same amount of attenuation as in the Firth of Thames site. So it's the channels that are providing a conduit for flow and are really sort of a path of least resistance through the mangrove forest. And people don't really recognize the importance of these channels in determining what kind of coastal protection they leave. Channels again. So I got really obsessed about channels and wondered, well, maybe they make a really strong difference to the asymmetry as well. And this is Min Radarian's PhD project. And here we are with our tidal stage plots. And this is the initial tidal stage plot, this blue line, and then we let it evolve. And so we let it evolve round till it's almost completely symmetric. And then we wiped out all the channels out of the bathymetry to see if there was any difference to the asymmetry. And there pretty much wasn't. It's really much the same. But what does make a really big difference, the channels, is other things like how the water is flushed through the coastal region. And so Min released tracer inside the model and tracked how quickly that tracer was flushed out. And you can see the two bathymetries here. One is with the channels, the blue, and one, we need a Q in equilibrium, never mind. And one is with the channels that have been totally eradicated in the model. And you can see the flushing characteristics are quite different. Without the channel, tracer is flushed more slowly out of the system. Now that's really important in terms of, first of all, fine sediment transport through the system, how long it takes to sediment out, and also all the biogeochemical processing, like the nutrients and contaminants and everything that moves in and out in each tidal cycle. And one more thing I did want to mention that I'm getting more interested in, and all these sites are really quite cohesive. The sediments are quite fine because of the low energy environment. And when we think about it, that becomes really important in the areas that are inundated and uninundated at each tidal cycle. And the sediments, even though the sediment characteristics can be almost the exact same. In the Firth of Thames, the sediment grain size is 4 microns almost everywhere, and it barely changes at all. But the erosion characteristics are completely different. And the reason why is every time it gets exposed, these cohesive sediments sit and bake out in the sun. And this is Hugh Nguyen, who just finished his PhD last year with me, and he basically did erosion tests on these sediments. So went and collected sediment cores out in the field and then brought them back in the lab and recreated atmospheric conditions. He used a cold room and low temperature ovens to bake the cores in different ways. So he treated them to 8 degrees Celsius, 25 and 40, and then ran this impeller, and there's a little optical backscatter sensor in this machine that allows you to work out what the sediment threshold is and the critical erosion bed shear stress. And so you could see that there was quite a strong increase in that bed shear stress, which is totally unrelated to the amount of chlorophyll or the sediment characteristics or anything. It just has to do with the binding of those particles when they get exposed to air. And he did a number more tests where he exposed it for many days, up to 14 days. And that exposure was meant to replicate the spring neap cycles that occur at the Firth of Thames, which has quite a strong spring neap cycle. So the areas in the upper reaches of the mangroves can be exposed to the weather from anywhere from 10 to 14 days. And he shows here's the critical erosion stress on this axis, and here's the erosion rate. So how much sediment gets scoured off the bed after the critical erosion threshold has been exceeded. And you can see that the erosion rate goes exponentially down as the exposure length increases, and the critical erosion stress goes up. So he's taken these results with the help of a colleague at Hohai University in China and incorporated them in Delft. And now we can actually model the effect of evolution, including this exposure effect in Delft. We've also done penetrometer effects, penetrometer studies where we've dropped penetrometers across the fringe and found that the penetrometer measurements agree with that. And either because of the root structures, which take a very long time, are very dense and fibrous, that reduces the erosion threshold as well. And the other thing is the dewatering. The trees dewater the sediments and reduce the amount of water in the pore, and that increases the erosion threshold and the consolidation of these sediments as well. So just checking the time. Oh, I'm doing perfectly. Very pleased. So in summary, just to finish up, I'll show you this picture of mangroves in New Zealand, because mangroves in a lot of our sites have been expanding. And in quite a few places, they're being managed by removal or seedling removal. And I think it's a good reminder that I've showed you all these natural considerations that we should look at in coastal adaptation models and incorporate. But I guess the final word is that we do have to remember that probably the biggest impact in our coast is not sea level rise or flooding or the subtle climate effects of baking and that kind of things. It's actually the really dramatic things that humans can do to our coast, like putting causeways, stop banks, and clear mangroves and that kind of thing. So that's it. I've got some acknowledgements. The experiments that were originally funded by Marsden, and my colleague Julia Malarney and Eric Horstman, who's now got a position back in the Netherlands. The work in Vietnam was with people in the States, Sergio Fergarazzi and William Narden, and Julia and Steve Henderson were doing the work in Vietnam. And Baron and Giovanni and Ian MacDonald have been working. They used to be at NE when we were doing this work. And of course, all the students, which hopefully I've acknowledged during the talk. And that's it. And I will unshare screen if I can work out how to do that.
All right.
Yep. Yeah.
Thank you very much, Karin. That was a very excellent talk. And yeah, we have plenty of time for questions actually and discussion. So.
Oh yeah, I finished probably a little
Anyone
fast.
has a question? Yes, Jeff Hansen.
Hi, Karin. Great.
Hi, Jeff. Nice to see you.
Yeah, how are you doing?
Good.
Quick question. So you talked a lot about the effect of the vegetation.